Welcome to The Explainer. Today, we're exploring a seriously fascinating new approach to giving robots and augmented reality devices far sight, all while running on a standard smartphone battery. We'll be looking at a major breakthrough in active geometry called DH-Active, and frankly, how it elegantly solves what's been a massive bottleneck in edge computing.
Here is our roadmap for today. We're going to start with the short-sighted LiDAR problem, meet DH-Active, and then break down exactly how its pipeline works. After that, we'll dive into the power of abstention, compare CPU geometry with GPU AI, and wrap things up with some really actionable takeaways for edge developers.
All right, let's jump right into Section 1, the short-sighted LiDAR problem.
To really set the stage here, we first need to understand a massive physical constraint in on-device spatial computing. If you're building a robot, or say an embodied agent that needs to navigate a physical room, it desperately needs to know exactly where surfaces are, and it needs to know that in actual physical meters. Now, active depth sensors, like the built-in LiDAR scanners you see on recent iPhones, are incredibly robust. They give you perfect metric data. But there's a catch. They have a notoriously short useful range. If a surface is distant, or highly reflective, or just at a weird grazing angle, the sensor just hands you an empty return. You are essentially flying blind beyond just a few meters.
Because of this, as an industry, we are currently stuck between two deeply flawed options when we're operating on the edge. On one hand, we have our hardware LiDAR. Like we said, it provides perfectly scaled metric data, but the range drops off a cliff after a short distance. Then, on the other hand, we have these massive learned multi-view neural networks and visual encoders. And sure, those models can guess the depth of an entire room, but they will absolutely drain your battery life, they require really heavy GPU compute, and crucially, they frequently just hallucinate geometry whenever they look at a textureless wall or an occluded area.
Which brings us to Section 2, Meet DH-Active.
So what's the fix? Well, here is the ingenious solution. Meet DH-Active. This is a training-free geometry backend that perfectly threads the needle between those two extremes we were just talking about. Instead of trying to train some massive neural network to just guess the missing depth, DH-Active brilliantly flips the script. It treats the active depth sensor not as the sole source of your depth map, but honestly, simply as a metric ruler. It uses the near-field points that the LiDAR actually can't see to mathematically scale the rest of the world that it can't see. And the best part? It does all of this entirely without machine learning.
Now, what makes this absolutely incredible is the speed. The core front-end pipeline runs at a median latency of just 1.11 milliseconds, and it pulls that off entirely on a standard CPU using OpenCV. Just to put that into perspective for you, in the author's testing, this core sequence is about 38 times faster than running a standard Dino V2 visual encoder on a heavy GPU. It uses literally zero learned parameters. That is a massive, massive win for strict edge power budgets.
Let's move on to Section 3, how the pipeline works. So you might be wondering, how exactly does a zero-parameter algorithm track a pixel and turn it into safe metric depth data? Well, the self-consistent loop works in three really elegant steps. First up, it samples the camera frame in a foveated spiral. That basically means it looks densely at the center of the gaze and spreads out, kind of mimicking biological vision. Second, it takes those nearby points that do have LiDAR depth to solve the perspective endpoint or PNP problem. This calculates the exact metric pose of the camera. Finally, step 3, it takes visually trackable points that are missing their depth data, and it triangulates their far-field position using that mathematically anchored camera pose.
Now, let's look at Section 4, the power of abstention. Because let's be real, in the real world, geometric reasoning breaks down all the time. Looking at the risk coverage data here, we can actually see this parallax and reprojection gate in action. And this is so smart. This gate explicitly discards bad data, or what we call ill-conditioned rays. If the math for a triangulated point is weak, say maybe there just isn't enough parallax between two frames, or the reprojection error is way too high, the system just abstains. Rather than forcing a really confident guess the way a neural network might, it just throws the point out.
The guiding philosophy here is essentially fail loud, fail localized. Instead of trying to forcefully interpolate missing values and potentially causing your robot to crash full speed into a hallucinated wall, DH-Active chooses to leave an explicit, structured hole. And that hole is accompanied by a selective confidence score. For safety-critical navigation, knowing exactly where your blind spots are is infinitely more valuable than having a completely filled in, but potentially totally false, map.
Okay, pivoting now to Section 5, CPU geometry versus GPU AI.
Let's look at the objective benchmarks to see what the actual trade-offs are. We definitely need to be impartial here. DH-Active is not setting a brand new state-of-the-art in raw accuracy. If you look at a 1.26 billion parameter model like VGT1B, it is absolutely more accurate. It comes in at a 2.5% median relative error compared to DH-Active's 6.7% on the AR-Kit scenes benchmark. But you have to look at the context. VGT requires a heavy GPU, and it relies on an external oracle scale to actually match physical metric space. Meanwhile, DH-Active delivers its metric sparse depth entirely on a CPU with 0 parameters, and it relies strictly on the device's own built-in sensors to establish that scale.
It's also really worth noting what doesn't work. The researchers thoroughly tested a bunch of classical alternatives. They tried single-frame defocus, classical focus stacks, blending defocus with LiDAR, and applying ICP over visual inertial tracks. And they openly report that these methods basically fell apart. They either collapsed under the sparse returns of consumer sensors, introduced uncontrollable scale drift, or they just swung wildly depending on the texture of the scene. This simple, gated metric loop of DH-Active was literally the only method that survived their screening for reliable far-field recovery.
Finally, Section 6. Takeaways for edge developers. So how can you actually implement this inside your own robotics or augmented reality applications? Well, if you want to use this pipeline because GPU compute just isn't available for your project, you're going to need these exact components. First, you need a PMP solver to anchor your near-field LiDAR data. Second, you need visual feature tracking for the pixels that are missing depth. Third, you absolutely must implement the validation gate to filter out bad geometry. And fourth, most importantly, you have to design your downstream system to handle missing data. If you just take this sparse depth and apply some naive hole-filling algorithm to it, you're going to reintroduce the exact hallucination problems that DH-Active was designed to avoid in the first place.
I'm going to leave you all with this provocative thought today. As we deploy increasingly autonomous agents into totally unpredictable physical spaces, maybe the pursuit of pixel-perfect depth is actually a trap. Perhaps having honest failure modes, structured abstention, and a system that has the ability to clearly just say, I don't know, are actually far more vital than hallucinated perfection. Thank you so much for joining me for this explainer, and we will see you on the next one.